All right, hello everyone, and welcome to the first of two lectures on distributions and descriptive statistics. My name is Tom, and I will be talking to you for about an hour now and an hour later about random variables, distribution functions, and functions of random variables. So let's get started. So what are descriptive statistics? Descriptive statistics, most simply, are summaries of data, or numbers about data, or descriptions of data. And specifically, they are just numbers about data or information itself, right? In other words, it's just this one set of numbers that you have and nothing else. So, in some sense, you can't use them for inference yet. Now, as we'll see, it's very tempting to use descriptive statistics as not just summaries, but for inference. And technically, we're not allowed to do that unless our data meets certain criteria. Right, so let's talk about some of the descriptive statistics that you're probably familiar with. There are two main types of descriptive statistics: location statistics, or we'll call them position related, and then dispersion statistics. Some examples of location statistics are means, right? Mean, median, and mode, our arithmetic mean and geometric mean. And some examples of dispersion are variance, standard deviation, the max and the min, kurtosis, and skewness. Just to give you a visual of what some of these look like, a mean would be if you have a set of points in 2 dimensions and you want to know something about, where is this set of numbers located on average, then it would be sort of a point in the middle that was equally distant or on average distant from all of those points. For variance, right, you can think about variance as if you have a distribution, right? And if the mean is its center of mass here, then the variance is a measure of dispersion, and variance is actually the square of this, so it's an area, and the linear quantity here is standard deviation. Those of you who know about things like standard error may notice that it is missing from this dispersion category, and that's because it's a measure of error about a mean, right? Not a measure about the dispersion of an actual set of numbers. Also on here, kurtosis and skewness are not necessarily simple measures of dispersion. Kurtosis can be thought of as a measure of how tailed some distribution is. So the probability of outliers showing up. And skewness is a measure of the symmetry of a distribution. So just to give you 2 visual examples of this, kurtosis would be if I have a distribution that looks like this, then something with a greater kurtosis would have more weight out here in the tails and much less in the center. So that the area here, right, the difference here is this area is here, and that's what kurtosis is about. Whereas skewness is about whether the distribution is sort of how symmetrical it is. Anyway, so these are some of the types of distributions or descriptive statistics that you've probably encountered before, depending on what age it may have been in middle school or in high school. But essentially, these are sort of the things that we have to work with when we're describing the numbers that we collect as scientists. Which brings us to the next question. Where do these numbers come from? Or where do numbers come from in general? And the answer is nature. They come from the natural world, and we measure them. There's some philosophical discussion about whether the natural world is in fact all numbers all the way down to the bottom. But for our purposes, whether the natural world is just numbers or something else, the only way that we as scientists get these numbers out of the natural world is by measurement. And what that means is that when we measure a process in the natural world, we see a set of numbers that comes out. In this case, I'm modeling some phenomena as a stream of zeros and ones that I want to measure. And we basically take these sets of numbers that we record from the natural world, and we try to model them to understand the phenomena that is going on. And one of the key tools that we use is statistics. And the things we're told, oh yeah, we use statistics. Statistics are one of the main ways that we use to model the natural world. And mostly we take that on good authority and say, okay, we'll believe you. We'll use these tools. But this lecture is really going to be about what actually allows us to use statistics to understand the natural world, and therefore about the mathematics that underlies the statistical tools that we use, so that we know when it's safe to use them, when it's not safe to use them. So the question is, what is this thing in mathematics that is equivalent to our measurement of the natural world? So what are the mathematical phenomena that are equivalent to the natural phenomena that produce the things that look like streams of numbers that we can do statistics on? The answer is random variables, and in this case represented by a capital X. And these are things that also produce streams of numbers that we can do statistics on. So that's a high-level overview of what this lecture is going to be about. But first, I want to walk through some of the notation that I'm going to use later in the lecture so that there is some familiarity with the terms that I'm going to use. All right. Notation. The first thing that we need to talk about is real numbers, and this is represented by a capital R, sometimes called a blackboard R. You may see me draw this like that, so it looks sort of like this. And some examples of real numbers are, negative 0.9999 repeating, 0, 1, 1/3, square root of 2, E, and pi. So these are sort of the general numbers that we learn to use in math. And that's represented by capital R. I'll just probably call it R, or the reals. And you can also then have, in addition to just a regular old number line, right? This runs from minus infinity to infinity. You can also have vector spaces that would be called R1, R2, or R3, or Rn. And in that case, it's just, let's draw R3, right? So in this case, we have 3 axes. That all go out to infinity, and you would have 3 points, 0, 0, 0. So this is just a regular old vector space. All right. Then we have sums. The next notation is sums, so this is the sum from I equals 0 to n of f of xi. In this case, the x's are indexed by I. The next piece of notation that you may see me use is the notion of limit. And this is the limit as x goes to n of f of x. And this is just the tendency of a function f of x as it approaches x. So to just draw this really quickly for you, if I have n out here and this is x along this axis, and f of x is on this axis, then in this case, this sort of says, okay, f of x goes to infinity, right, when x approaches n. So that's sort of what to think about when we have limits. Okay, clear this up. Next, integrals. So integrals these are both representations of integrals, and they're just area under curves. So in this case, a curve would be f of x. So if I draw f of x, right, if this is f of x, then the integrals are just this area under the curve. And in this case, this is called a definite integral, and it is from a to b. So it's just the area under the curve between 2 points, a and b. So then we have an indefinite integral, and it's just said this is the integral of f of x dx, and it's just this is equal to just some other function over here. And so that's just useful to know that you can just use the integral of a function dx, that is another function. All right, so that's sort of the basic calculus-related stuff that I wanted to cover, and now we're going to get into some more of the more statistics-related nomenclature. So some of you may recall from Kathleen's lecture the notion of a sample space, and she used this weird German S. I use omega, capital Omega, to talk about sample spaces. And those sample spaces are made up of elementary events, which I'm going to call little omega, right? So, and this is a theme that you may see in some of my notation. You have the set of all possible things being a capital letter, and then the instances within that being the lowercase letter. And we'll see this with random variables as well. So you have x, y, and z, or capital X, Y, and z being our random variables. And one of the notations you'll see me use later is you'll see me say something like, okay, x, capital X, the random variable, is less than or equal to little x. And little x is just a regular variable that is used to index this random variable. All right. So now we come to probability. And this is just read as P of A, or the probability of A. And you can put anything in there in place of A. You could have the probability of Tom wearing socks on a given day. Another way you might see this written is the probability under X of X, or Px of X, or and essentially this is saying this is the probability function for this particular random variable, which is sometimes can be useful if you're working with more than one random variable. The next piece of notation is the cumulative distribution function, or CDF, and it is represented by capital F of Fx of x, or just capital F of x. And this notation is pretty consistently used across many different textbooks that you might encounter. And sometimes I might say capital F under x, meaning that this is the cumulative distribution for this particular random variable x. All right. Next, we have the probability density function, or the PDF, and this is for continuous random variables. And we also have the probability mass function, or the PMF, which is for discrete random variables. and I'll talk about the difference between continuous and discrete a little bit later. Next up, we have, so the actual notation that is used for both of these, that I will use for both of these, is little f under x of x, or just little f of x. And sometimes you might see this written as little p under x of x, or just little p of x. Another important piece of notation is this squiggly line here. This is sometimes used as similarity or about, but in this case it means x, the random variable x, has distribution function normal mu sigma squared. So in this case, I'm just using the normal distribution as an example here to show that this can be read as has distribution function, or is distributed by. Okay, so next up are some of the sample statistics that we will compute, and this is the sample mean, or x bar, and s squared is sample variance. Lastly, I want to just cover some general notation that you'll see so that you're not lost. You may remember if you, from high school math, seeing this upside down A, which is the for all, or the universal quantifier. And so just to give a quick example of this, if you have for all x, where x is contained in R, right, then this is equivalent to saying that minus infinity is less than x is less than infinity. In other words, but it's all, like, it's every single one of these. And the last piece of notation I want to talk about are functions that map from domain to range. So in this case, we have x is a function that maps from capital Omega to R, or y is a function that maps from R to R. This could also be read as y is a function that maps from the reals to the reals. All right, so that's it for notation. And so now I want to motivate a little bit more, why are we interested in this? So what is the math that allows us to take a mean or a standard deviation and have it be meaningful? Said more formally, what is the math that tells us when it is valid to use a mean or a standard deviation? So this was the question that came up back on this slide here, which is, okay, no inference, right? So we're not allowed to use inference if we're just using descriptive statistics. The question is, when is this yet valid? This is the question that we're trying to answer. And so what I'm going to talk about now is the math that underlies this, that lets us do this. So the math that lets us do this are random variables. And random variables are, you could think about them as big collections of regular variables. In other words, they're at every single possible regular variable that could come out of some natural process at the same time. And we'll see what that means shortly. So regular variables are real numbers, right? They're 0, 1, pi, e. And we usually, as I said, we usually write them as little x or little y. Random variables, on the other hand, are functions, right? So they just like, they're like an f of x that you might see. So they're not the same thing as real numbers or as regular variables, but they do share some properties. So one important point that I want to drive home here in terms of keeping things clear and straight is that random variables are functions, but they're not functions that you can plot on a Cartesian coordinate system. Right? So normally you can plot a regular variable on this sort of, right? So if this is my x and this is my y, I can plot a function, right? This is f of x. I can plot that. Random variables are functions, but they're not the kinds of functions that you can plot easily in this way because they map from things that aren't real numbers to the reals. So again, one way to keep all of this stuff straight is to remember as we talk about random variables, their probability distribution functions, and their cumulative distribution functions. The random variables themselves you cannot plot on a graph. So I'm going to motivate random variables by building up an example which takes a sample space, a random variable, and the output of that, and use that to motivate some of our later thinking. The example I'm going to use is an experiment, right, or a sample space, which is a set of 3 coin flips. So let's look at this. All right. So that is our one instance of the experiment that we're going to be looking at here. In that case, that was 3 heads that came up there. But we want to know, okay, so that's what we're interested in. That's the event in the world that we're now going to model using a random variable. And that event, or the set of all possible events, I just showed you one tiny instance of that. And the sample space, which is some high-level Platonic representation of that, is our omega. We're then going to build the random variable x and the real numbers, which are what x maps to here. All right. So here is the representation of our sample space. So we saw with the 3 heads this instance here. This was the video where we had 1, 1, 1, 1, which was 3 heads. We're going to represent heads by 1s and tails by 0s. And so you will note that there are 2 to the 3rd total number of elements here, if you recall from Kathleen's lecture about counting. And we can go through and say, okay, here is each instance of where we had 1 head, 2 heads, 3 heads, and no heads up here. And the reason why it's 2, recall, is because we have 2 possible values that this can take on and 3 total. All right. So the question then is, for this random variable x, what does this map to an r? What are we going to map this to an r? And so I'm going to say x is the random variable that counts up the total number of successful trials or the total number of heads. And the total possible numbers of this are 0, 1, 2, and 3. And if we look, right, we're just going to split this out. Let me go back a slide. So in this case, right, x maps here. All 3 of these map to 1. The 3 of these map to 2. And 1, 1, 1 maps to 3. So that's sort of the basic overview of what x is doing. And so this is sort of, now I'm filling this all out. And I want to say, when I do this, recall there's only one 1 in R. And so I'm just doing this so that when I show you the map that X makes from omega to R, it'll be easier to see and think about. But I want to stress again, you can't count in R these 3 1s because there's only one 1 in R. Okay, so here's the map that X has. We have 1 that maps. Here's the 3 for 1 head, and here's the 3 for 2 heads, and here's the 1 for 3 heads. And so this is X, right? And so now we get some extra notation. X is the function that maps from big omega, our sample space, to the real numbers. And in this case, the values that X takes on are 0, 1, 2, and 3. Those are the actual values that X takes on. But it is the structure of X here, right? These 4 different colors and the number of colored arrows that is going to tell us about the probabilities of X that we care about, not anything in here in the reals. All right, so now we have the elementary events omega that we're interested in, which makes life a little bit easier as when we go to say, okay, how is X a function, right? Because I told you X is a function. But normally you're used to seeing a function written as, okay, where's this notation for X? And for that we need these elementary events omega. So I'm just indexing them here. So this is the first omega, little omega 1 is just represents these zeros. Little omega 8 represents all of these 1s, the 3 heads case. And so here now is the function that X is of omega. So X takes an elementary event and maps it to a real number. So in this case, we have X of omega 1 equals 0, X of omega 2 is 1, X of omega 3 is 1, X of omega 4, right, is 1, etc., all the way down to X of omega 8 equals 3. And so what are the guts of this function that let us do this in a more formal way? So in this case, we have X of omega is the sum, right? We've said we just want to add up all the heads, right? So we're going to sum up this function g, which I haven't defined yet, of for this particular omega over I. And the definition of g, which will make this make a little bit more sense, is that g of omega I is 0 if the ith flip for omega is tails, and 1 if the ith flip for omega is heads. So let's just walk through this with this example for W7. So in this case, we take g, right? We have g of omega 7, right, of I. And for omega 7, when I equals 0, this is this element here, g of omega 7 of 0 is equal to 1, g of omega 7 of 1, right, here, is equal to 1. Again, because we're saying this is another heads, g of omega 7 of 2, or sorry, 0 indexing, this is 1, this is 2, and g of omega 7 of 3. For the third flip here, we know we got tails, so this is 0. All right, so we come here, we say, all right, we got a heads on the first, we got a heads on the second, and we got a tails on the third. So that's how X works in terms of this mapping. But now we want to know how does probability enter into this? Because the reason why we're interested in X is that we want to be able to take probabilities of it. And so the way that this works is that we want to look at, let's say, the probability that X is equal to 3. So in this case, this is equivalent to saying the probability under omega, right, of the set of all omegas where X of omega is equal to 3. So let's look over here and we see that, okay, none of these are equal to 3, but this X of omega 8 is equal to 3, which means that this is equivalent to the probability under omega of omega 8. And this is equivalent to, again, the probability of the number of sets of 3 coin flips with 3 heads. And we say, right, that this probability here, this probability under omega, induces this probability under X. So that's just a term that is used to talk about how this works. Okay, so for those of you following along at home, you're probably saying, Tom, you've forgotten something really important. Where did this probability come from? Where does this probability come from? I can't, without knowing these underlying probabilities of getting a heads versus a tails, I can't actually calculate values for this. And so in this case, I'm just going to define probability of heads equals probability of tails, so that it's a fair coin, and that means that essentially we can just count these up, which will be useful as we go on. If these were not equal, then we couldn't just count the number of instances here. But because they are equal, the derived probability for all of these is going to just be counting. All right, because yeah. All right. So now that we've talked about probability and where it would come from in this case, let's think about the probability mass function for this example that we have here. And what it would look like. What should it be? Right? So we're going to start out with the 0th term here. What is the probability of this? Well, if I say, okay, we're just going to count this stuff up because it's a fair coin. There are 8 total things here, right? 2 to the 3rd, which means that the probability of this happening is just the number of times that it occurs, which is once. So it should be 1 over 8, right? This should be 1 over 8. And if we look, it is indeed 1 over 8, right? So then we come back here, we say, okay, so now we want to know what is the probability that X is equal to 1 and 2 and 3, and we just count them again. So this is going to be 3 over 8, this is going to be 3 over 8, and this is going to be 1 over 8. And as we step forward, we see indeed the probability that we get X is equal to 1 is 3/8, 2, also 3/8, and 3 1/8. All right, so now let's talk about the cumulative distribution function. here is the cumulative distribution function for x. And as you can, if you look carefully, you may, let's look very carefully, we will see, right, if I draw my lines here, that all, and then let's go back a slide, we see, okay, this matches exactly. Then this is the height of 1/8. This difference here is the height of 3/8. And this difference here, right, is a height of 1/8. So what we're doing, right, is we're just adding up each previous value of the probability mass function, and so it's just a cumulative sum of each of these. So if we just stack them all up, we get this value, the values that we see here for the cumulative distribution function. So let's dig a little bit deeper now and think about what that really means that the cumulative distribution is probably that x is less than or equal to little x. Because there's something interesting here, which is that I can ask this question: what is the probability that big X is less than or equal to E? And you may go, Tom, this is a discrete random variable. How can I ask this? Well, it works because of the structure that we defined for X here, right? In this case, this is why we mapped R, because over here, there is E. But there's no arrow defined from something to E. So it's just, right, there is no value, right? There is nothing here, right? Such that this will happen. Which means that when we put E on the number line here, we come and we look and we say, okay, well, how do we calculate this value, this probability that X is less than or equal to E? Well, we go along and we start at 0. And we say, okay, probability that this is the sum, and add all this stuff up to 1, probability that X is equal to 2. And if we wanted to, right, we could do probability that X is equal to 2.5, probability that X is equal to E. And the thing is that because of the structure of X, right, because of the structure of X here, this is equal to 0, and this is equal to 0. And these are the only ones that have any value, right? So this is equal to, right, our 1/3. This is equal to 1/8. This is equal to 3/8. This is also equal to 3/8. So in fact, this probability that X is less than or equal to little x is defined for every one of these. It's just that we don't add up all the infinite values between 1 and 2 or 2 and E because we know that they're equal to 0. The only points on the real line that have non-zero values are these 4 here, right? So you could also think of the probability mass function as just being, you could think of the probability mass function as being these points here. And essentially, these are the only values for which x is defined, little f of x is defined, all the rest are just 0. So we only need to add these 4 points together to create this cumulative distribution function. But nonetheless, we can still ask about points in any point in between. Okay, so now that we've sort of gone over the probability mass function and the cumulative distribution function, let's talk about, right, so we now have 2 additional things that we know about x. So I said x is a function, but we can't plot it, right? This is as good as we can do for plotting it. But we can plot the cumulative distribution function and the probability mass function for this. So let's look now at the more formal definitions of both the cumulative distribution function and the probability mass function, but in this case, no longer the probability mass function, but the probability distribution function, or the probability density function. So the probability density function is for continuous random variables, right? So unlike our previous example where we just had a couple points here, right, on the real line that had non-zero values, there's multiple, in fact, infinite number of points that have non-zero values. Which means that the way that we previously defined this function in terms of the probability that x is equal to x for continuous random variables, this is always going to be equal to 0, because essentially what this is the integral from a to a, right, of f of little x of x dx, which is just equal to f of a minus f of a, which is equal to 0. Which, and again, you can think of this as the fact that for any single point on this line, it's infinitely thin, so it can't possibly have any value by itself. Okay, what this means is that when we define the probability density function for a random variable, it's defined in terms of its cumulative distribution function. Specifically that it is the function f under x of little x which satisfies this equation here for all x. And essentially it's that, let's just walk through it with this example for the uniform. It says this is the integral from minus infinity to infinity. So when we integrate all of this under here, right, all of this value, everything else being 0, this is the only non-zero stretch. When we add all of this up, at each point that we come to, the area in here, if this is A, right, and then this is B, right, and we add up this area here, fx of A had better be equal to this area, and it is, right, and capital Fx of B will be equal to both of these areas combined, right? So it's just, we're going to add all this up, just like we did with the discrete case, but in this case we use an integral. Right? And so what this also implies, right, is that this function here, which is the probability density function, is the derivative of our cumulative distribution function. So let's go look at the uniform cumulative distribution function so we can see how these things are related. All right. So in this case, it's just the line y equals x from 0 to 1 because it's the uniform. And For continuous random variables, this is where the probability function enters in, because you can only really talk about x being less than or equal to our little x, our indexing variable. And essentially what it is just you get this line by saying, okay, what is the probability that x is less than little x? And for uniform random variable, the way that that's defined is you say, well, it's equal across the entire interval. And comparing these, you'll recall that from calculus, when you integrate a constant, right? When you integrate a constant, you get a straight line. Again, let's just one more time go through the formal definition of the cumulative distribution function. Capital F under x of little x is equal to the probability under x that x is less than or equal to little x. And so the reason why these definitions between CDF and PDF are not circular is because this probability function exists in here. And I can't really talk about how you get this line out of the probability function by itself, because that requires things like metric theory. So if you're interested in this stuff, you can take many more courses in this. All right. So very quickly, some of the things that relate the cumulative distribution function to the probability distribution function are the fact that the limit as x goes to minus infinity of f of x equals 0, and that the limit as x goes to infinity of f of x is equal to 1. This is for the CDF. Now let's look at this in this example here, right? So down here we have minus infinity. Over here we have infinity. And if we look at the values of this, here's 1 and here's 0. At minus infinity, this is still 0. It's 0 the entire way. So that satisfies that first example. And then over here at 1, it extends, the value 1 extends all the way out to infinity. So at infinity, this is equal to 1. So that satisfies that. And this is equivalent to this statement about the probability density function, which is that the integral from minus infinity to infinity of f of x dx is equal to 1, or for the PMF, that it sums to 1. And if we look at this, right, we know this is a nice example because for the uniform, this integral is really easy to do. We know that everywhere outside of this interval from 0 to 1, it's equal to 0. So all we have to do now is multiply, right? This distance is 1. This is also 1. Right? So we end up with 1 times 1 equals 1. And this is satisfied. The next is that f of x, capital F of x, for the CDF, is a non-decreasing function of x. Right? So what does non-decreasing mean? Well, here would be an example of a decreasing function of x. Right? On this interval here, x would be decreasing. And we can't have that because it ends up leading to negative probabilities in certain areas. So, right, we know that little f of x must be greater than 0 for all x. But if we know that right, if this is an integral, right, this is the integral of little f of x, then if we come over here, what that would mean, right, is that on this interval here somewhere, right, you would have to have a negative probability, right, and that's not really allowed. So in here, you would be calculating the probability between these 2 points, and you would discover that there would be negative probability, and so can't have that. Our notion of probability would break down; it wouldn't work. Let's work through an example of how to use all of this all these tools that we just built, the CDF and the PDF, to understand a random variable. In this case, it's going to be a normal 0-1 distributed random variable. Here is its probability density function. Here is its cumulative distribution function. One is right up here. Okay. So now we're interested in this question here. What is the probability that little a is less than x is less than b? And this is equivalent to these two statements here. The integral from a to b of f of little x dx, and this is also equivalent to capital F of x of b minus f of x of a. Right? So here's our integral. We just add all of this area up. And here's the equivalent here. And essentially, calculus tells us, right, because we know that this is an integration that's going on, we know that these two things are equivalent to each other. This distance here and this area here, they're equal. And this is useful to know because sometimes it's much easier to calculate the cumulative, or to look up the cumulative distribution function values than it is to integrate this little f of x. Right, and so just to walk through this one more time, x is our little indexing value. It indexes our random variable x so that we can ask questions about the probability of x taking on certain values. And that is represented by little f of x, which runs here. If you integrate little f of x, you will get capital F of x, which is this function here, and in which case these probabilities are represented as points on this axis here. Now, quickly at the end, we're going to go over some additional stuff about other useful things to know about distributions of random variables. In this case, joint distributions and marginal distributions. So I just want you to see this so that when people talk about it later, you've seen it and you have some familiarity with it. So if I have a random vector, right, in this case x, y, this is like a regular vector, except instead of regular variables, we have random variables. Then the joint distribution of x and y, right? So let's back up here and say, most times we don't just measure one thing at a time. We measure multiple things about nature at the same time, and we want to know how to model those things together. So we have x, y is distributed as little f of xy of xy, and that's the probability density function, or the joint probability density function, and this would be a joint cumulative distribution function. Capital F of xy of xy. And this is just the probability function now, a two-dimensional probability function, that x is less than or equal to little x, and y is less than or equal to little y. And then the marginals for this are just you just integrate out the other variable, and you get back the original density function for the random variable x, right? So in this case, it's just the integral from minus infinity to infinity of the joint under the other variable, and you do this for all x, right? And for y, you do that the other way. So I just wanted you to have seen this notation, and to know that, you know, this is often what we will deal with in a real experimental setting. All right, now let's talk again. You can have x a random variable x distributed as another random variable y. You can also have distributed as, in this case, a normal 0, 1. And those are going to be defined, those distributions are going to be defined, and you're going to interact with them in terms of probability based on their cumulative distribution function and their probability density function. Which brings us now to a very important point I want to make about distribution functions. When you start working with multiple random variables that aren't vectors, you have this notion of independent, identically distributed, or IID random variables. In this case, it's x1, x2, all the way up to xn are distributed as normal 0, 1 random variables. And it means that they don't have any interaction between each other. There's no conditional probability for any of them. And this is very useful. So what happens, and to see why this is useful, let's talk about what happens when you have failures of independence. Right? What happens when random variables aren't independent? Minus evil happens when they aren't independent. And this is because, if you remember the probability of the union of events from last week, probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. Right? So if A and B aren't disjoint, if this is not equal to 0, right, then that's what it means for things to not be independent. And it means that we can't just either add probabilities or think carefully about them because they are conditioned on each other. Right, and it means that if you wanted to know, right, if these weren't independent, then you would have to know a giant matrix, right, of x1 all the way up to xn, and here you would have x1 all the way to xn. You'd have to know the intersections values for all of these things. You'd have to know those empirically, and at that point, if you know all of that stuff, you probably don't need any statistics anymore because you've probably transcended the universe. Which is to say that you're going to have a lot of trouble using classical statistical methods to analyze your data if you think these things aren't independent. So we're going to jump in very quickly to functions of a random variable, and we're going to look at expected value and variance as examples of these. So remember, as I said way back at the beginning of the lecture, like regular variables, random variables can have functions taken of them. And in this case, we have an example in the expected value. And here we have the expected value of x, is the definition of it, is the integral from minus infinity to infinity of x times fx of x dx. Okay, so what does this mean? This is, you got to draw it to sort of be able to think about what this means. So it's essentially saying that, okay, you take the value at every point and you multiply it by its probability. So let's do this for the uniform. So here is fx of x, right? So this is fx of x, which is just the constant, and x. Okay, so here is x. This is x. Okay, so now let's multiply these together. Well, this is a constant. This is 1. So this means that this line here is their multiple, right? This is x times fx of x. And then we integrate it from minus infinity to infinity. Well, this is easy because it's just this area here, which is equal to 1/2. Right? So that's what this means. Similarly, if we were to do this for the example probability mass function that we used before, it just ends up being we got 1/8, 3/8, 3/8, 1/8, and you say, okay, and this is 0, 1, 2, 3. You're going to guess that it's going to be 1.5, and indeed, when you multiply these all together, you get 3/8 plus 6/8 plus 3/8 equals 12/8 equals 3/2 equals 1.5. So that's how expected value works. Variance, I'm not going to work out an example, but in this case, again, it's sort of similar. It basically says I'm going to take the integral from -infinity to infinity of this expected value that we had here and subtract it from each one of the values there and square it. So just to give a very quick visual of what this looks like, if I have a distribution here, and here is e of x, this is the value, then if I want to know the variance for every single point little x here, I need to subtract, I need to take this value here, right, and square it. And I want to know, yeah, that's essentially what we get. All right, so I'm over time, so I'm going to wrap up by saying, okay, this is the equivalent for discrete random variables. You just substitute the sum in for the integral sign. The very important thing to note here is that expected value and variance are not the same as sample mean and sample variance. They look really similar in principle, but they're not equal. So let's go look at how these are actually defined. The sample mean, which is the sort of classic mean that we think about, this is 1 over n times the sum from I equals 1 to n of xi. In this case, we're taking a sum of random variables that add up to this. This is not going to be the same as this expected value here, because this expected value operates on density functions, whereas the sample mean operates on random variables. Similarly for sample variance, this is operating on random variables, not on, the density function by proxy. And so this is where I'm going to end for this lecture by saying, here are the formalizations of sample mean and sample variance that we used, that we talked about at the beginning of the lecture, right? That we can actually measure on our data. These are examples of descriptive statistics, two sort of the classical examples that we deal with and learn about. The relationship between the expected value and the variance of a random variable and a sample mean when sampling from even the same random variable, they're not the same. And we'll talk next time, hopefully, about how we can make this link so that we can try and estimate things like expected values of the random variable from the samples, right? Because when we're sampling real data in the real world, we don't have the definition of xi here. We don't know what it is. All we have is this x bar. All right, that's all for now. I hope this was helpful, and I will see you next lecture.